I just wanted to start with this sort of picture of these different streams, because when we get into assessment and restoration and design, and especially talking about functions, Kurt mentioned stream functions several times, but that's a big term. So we're going to try to organize that a little bit as we walk through this presentation, because here are three very different streams. This is the Amazon River, this is a small headwater coastal plain stream, and this is Linville Gorge. So if we were just going to talk about the functions of each of those streams, in many ways they behave very differently. But in other ways, they behave very similarly. They all transport water. They all process or transport sediment. And they all provide some type of aquatic habitat or structure for biology that may be living in that system. But it's not always easy to communicate that, especially to communicate it with people who may have different backgrounds. And before I get into that, before we talk sort of about the structure of stream functions, I just wanted to back up and give a little bit of history. So if we look at sort of our relationship, the human relationship with the river, it's been warlike. If we look from 1820 to 1970, more than 200,000 miles of streams and rivers were channelized to reduce flooding, provide drainage and agriculture, and improve navigation. This was really how we thought of rivers. You know, if we go back, especially to the mid-1800s, rivers were there to be conquered. We needed to straighten rivers so that we could improve, and you'll see that word used a lot, improve the resource. And our definition of improvement was so that we could do human things, so we could farm the land, so that we could navigate the rivers and move goods up and down the river. And it really was about kind of conquering the river. And I think, in my opinion, is this 200,000 miles is probably a very conservatively low number. This is the number that's reported in Corps of Engineers and RCS federal documents, but private landowners were doing the same thing. They were channelizing streams. So that number is easily, I think, 2 or 3 or 10 times more than what we're seeing here. And how many of you have read a book called Rising Tide? Have you ever heard of that book? It's really a worthwhile read. It's about the 1927 flood, Mississippi flood, and it does a lot of things in this book. The first third of this book is about the goal of conquering the Mississippi. And it's back during a time when scientists were rock stars. So if you were a scientist, like, you were famous. And you had two guys, so it has all the good things of a story. You got, like, crime, you got fighting, you've got science. But it's a really cool description of some of these early engineers and scientists trying to figure out the hydraulics of the Mississippi River and then how to tame the Mississippi River. The original debate of whether to control a river with levees or not is described in this sort of historical book. It's a really good read. We got summer coming up, you're going to go to the beach, you need a good book to read, put this one on your list. If we could go back in time and look at a lot of these floodplains, we would see something different than what we see today. You would see, at least in alluvial valleys, and most restoration occurs in these alluvial valleys. So valleys that were built by the river, streams that would naturally be meandering. But that is not always the case. Is anybody here from West Virginia or do mountain work? So most of you are working more in alluvial valleys, meandering streams. So these valleys are usually less than about 2% slope. And if we could go back in time, we would see that these streams are kind of meandering down the center of the valley. There would be quite a bit of complexity on the floodplain in the form of old meander scrolls, natural levees. But the big thing about natural levees is they're not continuous on both sides of the river for long stretches so that they're containing floodwaters everywhere. You would have these wetlands or backwater swamps. You would have the connectivity and the interaction between the stream and the floodplain. If we sort of look at this in cross-section view, you can see that as well. So you have a small channel that's carrying water with access to these wetlands, oxbow lakes, backwater lakes, access to the floodplain. You get sort of natural sloughs, which are channels, old channels, maybe part of an oxbow that comes back into the stream, but it's not connected to the channel up above. And you do have this complexity, this river floodplain complexity. Well, that makes it hard to farm. So sort of, again, this historical perspective, that's a very difficult plan view and cross-section to plant corn on or to do any type of agriculture. The stream's all over the place. It's very wet. We're going to get our tractors stuck. So sort of the first kind of impacts were the channelization. So taking these meandering streams and straighten them so that we could move water more efficiently off the landscape and provide a place where we could grow our crops. And then we had people. So then we began to urbanize and grow that population, and most of our urban areas, especially here in the southeast, are superimposed onto that rural agricultural setting. So when we take Charlotte, for example, this is a picture from Charlotte, or Durham, or Raleigh, the urbanization has occurred. Usually channels have already been straightened. It's sort of, again, superimposed onto that rural landscape. Once we do this, once we take a stream that was meandering and we straighten it, that's kind of when the war begins. Because the stream does not want to stay straight. It has a lower slope, and it will try to re-establish that meandering geometry. And you can kind of see it here. If you look at this picture, do you see these sort of white areas? So those are alternating point bars. So this is a flood control channel. It was originally built to convey the 100-year flow. So it was kind of oversized. And then these depositional features have begun to form. That puts stress on the bank on the outside of these meander bends. So you have erosion that will occur here, erosion that's trying to occur here, and erosion that's trying to occur here as the stream tries to rebuild this new floodplain. Well, that kind of makes us mad, right? Because we don't want the stream eroding into our tennis courts. So this is sort of how the war begins. We begin putting hard structures in here, riprap, sheet pile, gabions, all sorts of things to try to prevent this bank from eroding. But in reality, all that does, when we take a stream that is systematically adjusting and we just stabilize one bank, all that does is transfer the energy downstream in this case. So if you did that here, you would prevent or slow down erosion here, but you're going to increase erosion downstream. We do know that channelizing streams, disconnecting streams from the floodplain, results in a loss of stream functions. It has been documented throughout the literature, and I've put some of the examples of papers that have documented those functional losses here. And a few examples are less water and sediment storage on the previous floodplain. That transport of water and the transport of sediment are functions. And channelization, by design, reduces or impairs those functions. And really related to that, when we channelize or straighten a stream, we also remove the complexity within the bed form. So we take out riffle pool forming processes, for example, and we replace it primarily with riffle, or the straight section of streams. A lot of the literature will call that habitat, but really what they mean is that bed form diversity. The diversity of riffles, pools, and wood, because we remove the wood from these systems as well. And just as you saw in that last picture, once we channelize that stream, especially in low grading environments, we encourage or we induce a response. And that stream trying to reestablish its pattern, it does that by more erosion. So you can have increased incision because the river slope is steeper, and you can have widening because the banks are so high. So we get both bed and bank erosion. And then really because of these things, we have documented loss of fish species and biomass. So this is important. The reason this is important is that I'm hopefully going to take us on a path to showing and talking about functional lift. So how a stream restoration project can improve stream functions. And we're seeing that already in the research that Kurt was presenting. But we kind of have to have this foundation and understand what can channelization do, what can incision do to lose functions. It's probably the biggest issue that we deal with as restoration practitioners, is trying to restore or improve functions in incised channels. All right, well, there's another study that I thought was very interesting, where Doug Shields compared a non-incised and an incised channel. They were not pristine watersheds. This was in Mississippi. Have any of you been to Mississippi? Hard to find a pristine watershed in Mississippi. You can find some very rural areas in Mississippi, but a lot of it's been farmed, a lot of it's been channelized. So he found 2 rural watersheds, not pristine, silviculture, agricultural watersheds. The big difference is that one was incised and one was not incised. And when he compared the two, what he found was that the incised channel had turbidity and suspended solid levels that were 2 to 3 times higher than the non-incised channel. He also found that phosphorus, TKN, total Kjeldahl nitrogen, and chlorophyll A concentrations were also significantly higher in the incised channel, and that twice as many fish species with 4 times the amount of biomass were located in the non-incised channel. So it really is just reinforcing the papers that we just saw, that incised channels lead to functional loss across categories: physical functions, hydrology, hydraulics, also biological functions with a fish.
Same amount of water coming down during storms and things like that?
Similar watersheds. So it's similar watershed size, similar land uses. All right, so I wanted to shift towards, I guess, begin talking about restoration. So that was just a little bit of the background. That really, as restoration practitioners, that's what we primarily deal with, are these incised rivers. And I also mentioned that historically, we, as humans, I guess, had this mindset of taming and controlling the river. And it was really about the mid-1900s, about 1980s, 70s maybe, we began to see this shift in philosophy, this shift that our rivers are more than a way to transport our waste, a way to navigate. It's just a disposal system. That it's more than that. We wanted more than that. We're starting to document these functional losses, and there's got to be a better way. And you heard Eddie mention Dave Roskin in the beginning. He really is, whether you like his methods or not, he really is a pioneer in stream restoration and sort of introducing a method called natural channel design. He began to shift this conversation from traditional channel design, which was to transport water quickly and the bed and banks don't move. How many of you are engineers? And how many of you had hydraulics in college? All of you. Okay, so I'm guessing, you can correct me if I'm wrong, but I'm guessing when you took your classes that the design goals that you worked with were primarily to move water. And you were given often a setup to design a channel that will move the QX. Could be the Q50, the Q25, Q100, but that was really the setup for your design. Is that right? Yeah, because that's still sort of that. If you read Rising Tide, you see the beginning of that philosophy. That is born in this mindset of drainage, of flood control, drainage, moving water. And the definition of stability is that the bed and banks don't move. That's why you end up with this trapezoid channel and why concrete is acceptable. Concrete has a stable bed, a stable banks, a low friction factor, so you can move a lot of water and keep things stable. And really, Roskin began to shift that discussion to what he called natural channel design, and this term basically his design goal shifted from this to creating a stable geometry, which he split into dimension, pattern, and profile. So dimension is the cross-section of the stream, pattern is your plan view, and profile is the slope. So you create a stable dimension, pattern, and profile so that the stream does not grade, which is fill up with sediment, or degrade, which is erode. And that was supported by a lot of people, a lot of agencies, I mentioned from the discussion that a lot of the permitting is kind of split between restoration, you just maybe need a nationwide 27 to get a stream restoration project, to mitigation, which means you got to go through an interagency review team or a different process to make sure that your project can produce credits. And a lot of those mitigation SOPs in terms of doing restoration are founded and built on this definition, that doing restoration and getting the most credit means making changes to dimension, pattern, and profile, which inherently is not that bad, but regarding functions, it has led to some unintentional consequences, and we'll talk about that as we move forward. All right, so I want to just talk about what is restoration. So this is there are a lot of definitions. I'm going to go over two definitions. This is a definition that's out of the 2011 book called Stream Restoration and Dynamic Fluvial Systems. And it says that stream restoration is a catch-all term used to describe a wide range of management actions and as such is difficult to define. The definition of stream restoration can vary with the perspective or discipline of the practitioner or with the temporal and spatial scale under consideration. So that's a lot of words. That means it's really pretty hard to define. And based on your academic background, based on your job experience, and I would add based on where you work, the landscape settings that you work, you will have perhaps a different definition of restoration than I may have. But there's also regulatory definitions. How many of you work in mitigation? Do most of you work in mitigation or not work in mitigation? So actually, there are more here working not in mitigation than working in mitigation. If you do work in mitigation, you work under the we all work under the Clean Water Act for permits, but for mitigation, we also work under a federal mitigation rule that defines definition this way, restoration this way. So it says restoration means the manipulation of the physical, chemical, or biological characteristics of a site with the goal of returning natural/historic functions to a former or degraded aquatic resource. And then they lump reestablishment and rehabilitation underneath there. This definition doesn't help a lot from the past definition because to me, it still has two pieces. And I think for clarity of communication, we have to split these two things out. And we have to be crystal clear when we're talking about restoration, which of these two things are we talking about? Are we talking about restoring lost functions, which could be a whole range of things? We could restore floodplain connectivity, we talked about. That it would be restoring functions. Has nothing to, well, it is not the same as saying you're going to restore a fish species. But it could, if we're not explicit in what we mean, you could confuse people if you just say we're going to restore stream functions because it's so broad. We're going to talk more specifically about that. Or restoration could be restoring to a pre-disturbed condition. That's kind of the ultimate, right? That's the ultimate definition of restoration is we will restore to a pre-disturbed condition. We will take the Mississippi and make it look like it did, 400 years ago, 500 years ago, which actually would resemble the Amazon basin, just much smaller. There are a lot of similarities in the characteristics of those watersheds other than size. That's probably not feasible. Not only could you not do it because of the conflicting goals, no one would pay for it. So we have to really understand from the beginning, are we talking about restoration in terms of restoring to a pre-disturbed condition, or are we talking about the restoration of functions? And for kind of the rest of my talk, and I am going to, believe it or not, at some point tie this back to the swamp and Duke Forest, but we are, and 9 out of 10 times, what we're really talking about is restoring specific functions. Okay, I want to kind of revisit that stream perspective thing. So this is also key. Even with restoring stream functions, what's going on in your head, the pictures that are in your mind right now are varying by your discipline and your experience, and maybe where you're from. So if you're like a Barbara doll, except Barbara's multi-talented, so she's not really a good example. But if you just asked, maybe if you asked Barbara I shouldn't say that, a few years ago when she graduated college, what was the definition, what's the function of a stream? If you're a classically trained hydraulic engineer, what would you answer?
It just gets rid of stormwater.
Transport water.
That's when the transport commission thinks the stream is.
Well, do you think that is correct or incorrect? Is a function of a stream to transport water? Yes, a function of a stream is to transport water. The, big capital T, the function of a stream to transport water is a limited view, right? It's much more than that. If you ask a geologist, this would be sort of the geomorphologist, that's my background. If you ask one of us, what's the function of a stream, what do you think we would say? Yeah, we would probably say something like, a major function of a stream is to transport, store, process sediment and wood. We are most interested in why streams look the way they do. And are those functions of a stream? They are functions of a stream as well. Well, what happens when you ask an ecologist, what's the function of a stream? Well, first of all, you have to pull up a chair, right? Because you're going to be there for a while. They're going to run their mouth for a long time. They're going to talk about the life histories of this bug and this fish and stream metabolism and nutrient cycling and how habitat's important and linked to all that. And then they're going to see a butterfly fly by and they're going to be distracted by the butterfly. You're going to have to pull them back around and get them to focus again. But they're going to talk about all those interactions of things that go on in the environment. And are they right or wrong? They're definitely right. But it is these things together. These are all functions. And I think one of our biggest challenges, one of the reasons that you will hear people say stream restoration does not work is because they're living in their little box and they're coming at it from one specific perspective. So I'll give you a quick story, my favorite perspective story. Some of you have heard this before, so you can tune out if you want. But I was working in Alaska last summer with the Bureau of Land Management. We were incorporating the framework that I'm getting ready to show you into their program. And I was having breakfast at this hotel, and this waiter was, I think he had just graduated high school. So a young guy, I was in Fairbanks, Alaska. We're chatting, and I said, so have you lived here all your life? He said, yes. I said, it's got to be hard when it's dark for 24 hours a day. And he said, it's all I know. I was born here. I've lived here all my life. He goes, what's weird to me is when I go into the lower 48 and it's dark and warm at the same time. He goes, that just freaks me out. And I'm thinking, have you ever had that thought? I have never in my life has that thought even sunk into my consciousness that being dark and warm at the same time would be a strange thing. Because in the summer, it's light the whole time. It's warm, and in the winter, it's dark the whole time, mostly, and it's cold. And I'm thinking, that's just like stream restoration. You were thinking that too, right? It's just like stream restoration. Like we come at it from these different boxes, and it's hard to get out of those boxes and realize that someone may be thinking about functions a little bit differently. So just one more kind of case in point. This is a stream restoration project in the coastal plain of North Carolina, a pretty classic stream restoration project by North Carolina standards. This was a channelized stream, a lot of lateral ditches coming into it. It's about 6 miles long. A much smaller meandering channel was built, well connected to the floodplain. I am hoping that everyone in this room, this is taken soon after construction, so the trees aren't in yet. But I'm hoping that you would look at this picture, and if nothing else, you would say, yes, that is stream restoration. Well, in 2010, Civil Engineering Magazine came out, and in fact, they interviewed a number of us in the restoration community and asked us about stream restoration and said that they were going to produce a magazine with an article on advancing river restoration, which I found fascinating because this is the same organization that has training courses on channelizing rivers. So now they're going to, get with the times and offer advancements in stream restoration. So if you flip through the magazine and you get to the cover article of their story, this is the definition of advancing stream restoration. This was their project that they highlighted and put on their cover. Does that look like stream restoration to you? There is a riparian buffer. There's a couple of trees planted. And apparently this general path is an old oxbow pond that they are converting into a park. And their reference reach was the Riverwalk in San Antonio, Texas, if you've ever been to the Riverwalk. So they used the right buzzwords. They have a reference reach. They had some function, right? They moved water. I think they pumped it, actually, from the river into this oxbow channel, and they have some plants. They even have some dissolved oxygen creation there. But I think most of us would not agree or not feel that this would meet a restoration definition. I'm hoping that you feel that way.
Where was that supposed to be?
I think this is either in Arkansas or Oklahoma. But this is a rendering. So at this point, it had not been built. I have no idea if it ever did.
They probably met the goals of the township supervisors.
Oh yeah, absolutely. I would assume as well that the goals of this project had more to do with recreation, tourism, economic development than it had with having a certain fish species back into their rivers. So I am not saying it's an unsuccessful project. I would argue that it is not advancing stream restoration, which is what the article was about. Okay, so this is the framework that I mentioned that I want to walk through. So the real purpose of this framework is to help bring the disciplines together and provide us a very simple thought process for communicating stream functions and acknowledging that all functions aren't created equal and that there is a hierarchy, that some functions support other functions. And as we move into assessment and restoration in particular, this structure can help us set goals, help us do assessments, and help us measure functional lift. If you are an ecologist, or anybody else really, and your purpose in life is to study all of the interrelationships between functions, this is not a structure for you. It does not go there. This structure is a simplification and a way to help us think about if we want a function, what supporting functions do we need in order to meet that goal? That is the primary purpose of this framework. So if we kind of just walk through it, it starts with geology and climate, really even below this pyramid shape, and acknowledges that all of these functions are going to be shaped and affected by that local geology and climate. That's why streams in the southeast look different than streams in the southwest. We are a very humid region. They are a very arid region. Our limestone, for example, is valley forming here. Their limestone is the tops of ridges. So that geology and climate shapes everything above it. And this is where discussions of climate change could come in. How might climate change run all the way through this pyramid? So the first level of this pyramid is the hydrology function. And we call this a functional category. Hydrology would be a functional category. And with each category, we put a functional statement. So the statement that goes with hydrology is that it is the transport of water from the watershed to the channel. That is the function of hydrology. Once we have the watershed producing a certain amount of water that reaches the channel, then we have hydraulic functions. And that is the transport of water in the channel, on the floodplain, and through sediments. That's where action begins. Velocity, shear stress, those energies are seen in the channel. Once water is moving in the channel, work can be done. That typically is the geomorphology function. So the transport of wood and sediment to create diverse bed forms and dynamic equilibrium. And by the way, transport of wood and sediment could mean a transport rate of almost 0. We've had a few people look at this and say, well, your geomorphology functional statement is assuming sediment transport. It really is not. It is acknowledging that if there is a channel present, sediment transport occurred at some point. There was an erosional feature, but it certainly could be that today's rate of transport is near 0. That still fits in this box. And then on top of the geomorphology is the physicochemical. So the temperature and oxygen regulation, the processing of organic matter and nutrients. So you could say, well, hold on. If you would have temperature as soon as you had water, right? That is correct. But again, the purpose of this framework is to provide a thought process for assessment and design. So the way you would do that, or the way you should think about these functions, is that if you wanted to change the temperature regime of a stream, what changes to functions would you make in order to have that? And that would occur down here. You would have changes in your geomorphology, changes in your hydraulics in order to change that temperature. That's the way this works. And then at the top is biology, so the biodiversity and the life histories of aquatic and riparian life. So in order to have the healthy biology, you need to have the supporting functions underneath it. That's how it works. It doesn't mean biology is more important than the other functions. It also doesn't mean by a pyramid shape that there are more hydrology functions than there are biology functions. It's set up as a pyramid simply to show that the lower level functions support the higher level functions. And if you want functional lift or improvement to higher level functions, you need to think about the lower level functions. How do you get the lower level functions?
Is there any correlation between sediment transport and the number or the diversity of bugs in the stream and trout? In other words, if you have a stream that transports a lot of sediment, I don't see how the insects can survive because they're being washed away at over 5 foot.
Right, so there are a few steps in between, but yes, so sediment transport can certainly affect macroinvertebrates and fish. And the way that works is that the sediment transport, if you have too much sediment transport, you could have degradation. That could lead to channel incision, higher velocities in the water, could erode those habitats that are needed for macroinvertebrates, for example. On the flip side, if you had too much supply of sediment and not enough capacity, you could degrade your pools, lose the bed form diversity, lose the habitat, and then lose the bugs. So it's not a sort of a one-to-one. It's not that you change sediment transport and you immediately would see a change in bugs. It's that as sediment transport gets out of whack, it affects things in this category, and then ultimately in that category. So as a framework, generally, we should think about lower level functions being more about cause and the higher level functions being more about effect. This is a critical thought process for practitioners because we may enter a project and the goal of that project may be to restore a fishery or to restore macroinvertebrates. But how are we going to do that? Like, we're not going to take buckets of fish and dump them into the river and say, you're restored. Good luck. I hope you do well. Right? And we're not going to make fish. But what we can do is we can manipulate the functions in these lower level categories to create the right conditions for fish. But there's also the watershed as well, right? So one thing I want to talk about as we move forward is the reach and the watershed. So if we sort of split this up, the hydrology functions are typically independent variables for the practitioner. Please, if you're taking notes, star, underline, circle the word typically, because I get beat up sometimes with this slide. And what I mean by typically would be a stream restoration project that is in the middle of a watershed. So you're not restoring or treating the entire watershed. You have a reach. Maybe you have a 5,000-foot reach in a 4 square mile watershed. So you would calculate the hydrology of that watershed. You would measure the hydrology, but you're really not going to change the hydrology. It is an independent variable that you enter or bring into your design. Now, the reason I say typically is that some of you I know who work in urban areas sometimes can work in the headwaters, and you may be doing restoration of the entire watershed. Maybe it's a half square mile or 1 square mile watershed. And if you're doing that, and maybe you're doing a combination of stream restoration and stormwater BMPs, the stormwater BMP part certainly can change the hydrology. So it is possible. It can be a very good thing. You could argue, depending on where you live, which is more typical. I think nationally, as you look at restoration projects, it is still atypical to be able to restore an entire watershed. All right, the reach scale restoration that you'll see people do is really in levels 2 and 3. Practitioners have a lot of control over their ability to manipulate or change hydraulic functions and geomorphic functions. The floodplain connectivity we talked about, a hydraulic function. The bed form diversity, the lateral stability, the riparian vegetation is the geomorphology. We can affect all of those things. We have very little control over the physicochemical and biology. Now, we do have some. So, for example, as Kurt was showing with his data, as you continue to add more projects, so your reach becomes bigger and you add stormwater BMPs and stream restoration, your ability to change physicochemical parameters like nitrogen, like phosphorus, like bacteria increases. And same with biology. But generally, at least as a thought process, if our intent is to restore physicochemical and biology, we should be thinking about site selection in addition to the reach scale improvements. If we want to restore a fish species, and we're only working in 3,000 feet of stream, for example, the chemistry of the watershed needs to support that fish before we fix the reach. Because we can fix the reach, but have no control over the chemistry coming into that reach. So that's why they go together. And you can kind of split these out by thinking of hydrology as independent variables, the action, the restoration action in levels 2 and 3, and then the site selection thought process for achieving the 4 and 5. And yes, they do all go together, but you kind of split your thought process this way. Okay, the framework itself kind of looks like this. What we just talked about was the broad level view, and that includes the functional categories and the functional statements that we just went over. And then it really is a drilling down into more detail. So after that are function-based parameters, and these are parameters that we can measure that describe or support this functional statement. And then in more detail underneath that are measurement methods. So the measurement methods quantify the function-based parameter, and then where we could, we put performance standards attached to the measurement methods. And then we put them into buckets of functioning, functioning at risk, and not functioning. So I'll kind of give you some examples. If we walk through this, the 4 function-based parameters for hydrology are channel forming discharge, so like bankful discharge, precipitation runoff, flood frequency, and flow duration. Those are all parameters that help us understand how much water is being produced by the watershed. As we move up, the 3 function-based parameters for hydraulics are floodplain connectivity, flow dynamics, and groundwater surface water interaction. The floodplain connectivity you have heard us talk about a lot, and you will continue to hear us talk about a lot. It is one of the biggest drivers of all of the functions from here up through biology. Geomorphology has the most parameters, so we have sediment transport, large woody debris transport and storage, channel evolution, bank migration, so that's the lateral stability. riparian vegetation, bed form diversity, and bed material characterization. Does it freak you out a little bit that I put riparian vegetation in a geomorphology bucket?
I like it because I was having a problem. I was going to ask you about riparian vegetation. I was like wondering, you know,
Where to put it? Where to put it?
Yeah, just a canopy.
So that's one function. The reason that we put vegetation in geomorphology was twofold. One, the importance of that riparian vegetation on channel stability, which is within the geomorphology level. The other is that riparian buffer, the width of that buffer, the age of that buffer, the species that are there, has a lot of influence on the physicochemical, the level 4. So you have to have, in many cases, that riparian corridor first before you would begin to see, the denitrification, the temperature regulation, and those things. So we put it in the geomorphology bucket.
It's often treated as a boundary condition. Like
Roughness.
regime work.
Yeah, and that, so that's an example. So you could say, well, that's an example where it actually comes down, right?
Right.
Your geomorphology absolutely can affect your hydraulics, both from a roughness perspective. The sinuosity, which would be here, can affect hydraulics. The reason, and there are many examples, like you could even say biology. Think of a beaver. A beaver is biology. It can affect all the way down through the pyramid. It can affect hydrology, flow duration, right?
Well, as an ecologist, you need some feedback with some area.
I really don't. I know that you guys want that, but I really don't, and here's why. And that's why I said if your job or your mission in life was to study all of the interrelationships, this really isn't the framework for you. But if you wanted to ask and so beaver is a great example. Beaver can affect all these things. But if you ask the question, what do I need to have in order to support beaver, this structure works. You still have to have a certain physicochemical regime. You still have to have a certain geomorphology. You have to have the hydraulics, water in the channel. You have to have water being produced by the watershed. So that's the thought process for this framework. Now, I don't really know why you would ask the question, how do I get beaver in here? Because they come. Although there are places in the country where they are looking at that as their primary restoration method. So some people do ask that question. But that is the difference, is that we are using this structure to organize the parameters that we want to measure, and more importantly, the parameters that we may need to manipulate in a design in order to achieve a goal. And that's where the value. You start putting those feedback loops in there, you can't make a decision. You're like paralyzed. Like, have you seen those diagrams? Like, there are arrows going everywhere. You're like, where do I start? So this has a very specific purpose in mind.
In building riverbank vegetation, has anybody done studies of succession? In other words, you could put trees in, but it's going to be a long time really before so you could start up with ground cover and shrubs, and then eventually the trees take over and do it. Has anybody done that kind of studies to know how to really do it from scratch? You're taking a bare field and making it.
Well, there have been studies that have said, how long does it take this buffer to grow before I see improvements into things like macroinvertebrates and water quality? And the answer, at least with the one study that was in the Chesapeake Bay area, was about 10 to 15 years. So at about 10 to 15 years, they were seeing restored streams begin to behave similar to reference conditions from a macroinvertebrate and a RBP score perspective. Okay, so the physicochemical parameters are water quality, nutrients, and organic carbon. I should mention here that these parameters are all considered examples. So if you wanted to add metals, for example, or you wanted to add parameters, you can. The thought process or the method or criteria for doing that is that your parameter needs to describe the functional statement within that functional category. And then biology. So we put bugs, fish, microbial communities. You could add mussels. You could add beaver. I got a call from the World Wildlife Fund. He wanted to know if they could add add elephants. and he studies elephants in the Congo. I told him I'm not sure, but if he took me to the Congo to see elephants, I'd let him know. I haven't heard back. And we also put landscape connectivity here, and this might freak you out a little bit too. Like, why would you stick a physical thing up in a biology camp? And the reason is that when we started researching all the ways to measure landscape connectivity, it was all driven by a species of interest. So you had to pick sort of the species that you were interested in. Is it fish? Is it a turtle? Is it amphibians? Is it bear? Birds? Whatever it is. And then the criteria for what makes up that sort of habitat gets fleshed out from there. So we put it up here to acknowledge that. So it's not just about connecting crappy land, it's about connecting landscapes that support that species of interest. So you would have to have all of these things in place before the landscape connectivity would function at the highest level. Okay, so if you want more information on this, you can download this document. It's like a 340-page document that we just went over in 10 minutes. You can get it from my webpage, or you can get it from EPA's webpage. We also have on that the work that we did to develop this was supported by EPA, Fish and Wildlife Service, and the other tool that went with this was a review checklist for natural channel designs. So if any of you are reviewers, like in an agency or even within your company, and you have to review natural channel designs, this is a checklist that you can use. All right, so now moving into applications and getting slowly to the sites here on campus. We also just want to acknowledge, I mentioned incision, but there are lots of issues that we deal with, from the channelized streams and Mother Nature fighting back, to we still have obviously lots of agriculture, lots of drained streams, channelized streams, lots of incision. We have changes in our watersheds going from rural to urban, so urbanization issues, dams and dam removal, other forms of blockages like culverts. We still have runoff issues from cropland, runoff issues from urban areas, and mining. So we have, and this isn't a comprehensive list, lots and lots of impairments or impacts to deal with. This sort of takes those and puts them into two camps of direct and indirect. So if we look at the impacts to our channel, direct impacts, I mean, it's in a literal sense of the term, we are directly impacting the stream, would be things like regulating flow, so dams, channelization and levees, in-channel mining, so removing sediments, sand, for example, gravels from streams, beaver trapping, removing beavers, wastewater effluent. I was in a city once, they asked me to look at the stream to see if we could do stream restoration, and the channel itself wasn't in that bad a shape, and they were saying, hey, maybe we could do some habitat features. And I noticed the stream didn't smell very good. So I was like, are there wastewater treatment plants upstream? And they were like, oh yeah. I'm like, well, what % of the flow that we're standing in is coming from a wastewater treatment plant? And they went, 99%. I'm like, do you have bacteria problems? Oh yeah, it's on the 303D list for bacteria. I'm like, you got the wrong guy. Like, I can't help you with that. Like, putting in some logs and creating some pools, like, spend your money on wastewater treatment. Like, you got bigger problems here than habitat. So that is a direct impact. Floodplain encroachment, building in our floodplain, filling our floodplains, snagging and removal of wood. These are all direct impacts to the channel. But then there are indirects as well. Timber harvest. So indirect essentially are changes in your watershed. So the timber harvest, agriculture, urbanization, and I added mining as well, because that can be not only a direct impact, but also an indirect impact, like surface mining. Do any of you have to work in coal mine country? Consider yourself lucky. All right, so how can we use this pyramid? Well, I'm going to go over the two examples. I'm not going to get into debit and credit determination because it's associated with mitigation, and none of this work is mitigation related. So we'll talk about goals and objectives a little bit, and then about assessments. All right, so if you look in the literature, one of the most common goals for a stream restoration project is the goal of this project is to improve habitat. How many of you have seen that goal? quite popular. Well, I say that is a bad goal. And the reason that is a bad goal is that planet Earth is habitat for something. Like you can find some living organism at the bottom of the ocean and on both poles. Like that's a bad goal because you're not specific. So it's sort of the habitat for whom. So a better goal might be if you were working in the habitat, it's not, I guess I'm being hard, beating up on habitat. It's not so much that the habitat goal itself is bad, it's just that you have to be specific. You know, so call out who the habitat is for. So here's an example. The goal of this project is to improve native brook trout habitat. Now, this is still a level 3 goal. Habitat is, on that framework, level 3. It's really bed form diversity, channel complexity. It is not level 5. Habitat is not the fish itself, it's the home the fish lives in. So it would be level 3. And you could do that. You could go into a reach and you could put in the habitat that is appropriate for the native brook trout. And they may or may not come. I put even better. I get beat up on this too. Maybe you could replace better with more specific or a level 5 example. I try not to be judgmental between whether a level 3 goal and a level 5 goal is bad or good, but the real point is they are different and they should have different expectations. So in this goal, you've said the goal of this project is to increase the biomass of native brook trout populations. Once you make that change from a habitat goal to a life histories goal, you went from a level 3 endpoint to a level 5 endpoint, and you better well know that your watershed will support that goal. There is a project in Baltimore where they had this goal. They had this goal, but they did not have that watershed. They had Baltimore as their watershed. They went in and they did, I've never seen the project, by all accounts, they did a good project. They sort of followed the standard of care for stream restoration. It had floodplain connectivity. It had bed form diversity. It had a riparian vegetation. People looked at it after the project and they said, this is good. And no brook trout came. So the project was a failure. And in fact, the paper that was written did not just say this project is a failure, it said stream restoration doesn't work. Because they had spent a lot of money, they did stream restoration, and no brook trout came. When you peel back the onion a little bit more and you started looking at the watershed, you could see buffers leaving the project and going upstream in the perennial stretches. I don't know the designers, but I'm assuming that may be why they thought they could get brook trout. But what they didn't pay attention to, if you look at the land use change over a few decades, you could see it going from forested, when native brook trout were there, to suburban and commercial. And if you go and dig a little bit more, you see lots of ephemeral channels coming from parking lots, roads, and buildings right through the buffer and into the channel. The temperatures were too high.
So when you get into those kinds of details below that first onion skin, and
Yeah.
if you're looking at a nonprofit environmental organization, eyes glaze over. Beyond that.
Why do what say that?
Their
Why?
eyes glaze over when you get into details and maybe quantitative objectives.
Well, their eyes may glaze over in the beginning, but their wallets hurt in the end. Because
I agree, but I can tell you how it is at the beginning.
Yeah.
They don't want to get into that.
But they have to. You absolutely have to. And this wouldn't be that hard. You're not talking about a lot of detail here. This was just talking about understanding that will your watershed support this goal, or will your watershed support that goal? The same reach. You could have the same project, but if your watershed will not support it, then you may need to change your goal. I'm not saying to not do the project, because it takes both. You could have done that exact same project and just change the goal that we are going to provide. The piece that we can provide is the structure, is the level, the hydraulics that a brook trout need, and the geomorphology that a brook trout need. And then you go to the sponsor and you say, but you have more work to do. You're going to also need to do stormwater BMPs. You have a watershed scale effort that you're going to need to do to keep these temperatures below 70 degrees Fahrenheit in the summer if you want to see your brook trout. So I'm not saying not to do it. I'm saying understand your limitations and be specific with your goals so that people then don't come back and say stream restoration doesn't work. That was really poor, in my opinion, of the authors of that paper. That's a huge statement. Stream restoration doesn't work. What they really meant was this project didn't meet its goals. And what they really meant was that if you wanted to meet the goals, you would have to treat the watershed and the reach. And some people make the mistake, they go straight to the watershed. And they're like, oh, we got to work in the watershed. It is both. As Kurt's showing with his data, making these changes to the habitat do make a difference. It's sort of, have you heard the criticism, if you build it, they will come, and it's sort of the pipe dream and blah, blah, blah. Well, if you don't build it, they won't come. It is both. It is the reach and the watershed. Okay, another bad goal is the goal of this project is to improve water quality. How many of you have heard that one? That's another very popular goal. That's a bad goal as well, because water quality is just as broad as habitat. So are you talking about making improvements to temperature and dissolved oxygen? There actually are quite a few things with reach scale restoration that we can do to improve temperature and dissolved oxygen. But we need a long project in order to do it. Or are you talking about pH and conductivity? There's not a whole lot that a restoration project can do to change pH and conductivity. We might, if there's a lot of non-point source pollution, maybe we could see a bit of a bump in conductivity, but it is generally a reflection of your watershed, both the geology and whatever's going on upstream. And then, as we talked about here, nutrients, nitrate, nitrogen, phosphorus. If that's a goal, then you also need, as Kurt was alluding to, you really need stream wetland complex. You need to get water out of the channel and onto the floodplain and get groundwater surface water interaction taking place and get a buffer that has roots that are in contact with the water table. So a better goal, water quality goal, might be the goal of this project is to reduce nitrate nitrogen from adjacent land uses. I put the word adjacent in here because we have a better chance of seeing nitrate reduction in a stream restoration project from lateral sources than as a treatment for the watershed, so what's coming in upstream. And then we can become even more specific with our objectives. So improving bed form diversity, which is level 3. Establishing a 100-foot riparian buffer, a level 3 parameter. Provide floodplain connectivity, level 2 parameter. Improve groundwater surface water interaction, level 2. So the goals can still be kind of broad, and the objectives are getting much more specific and are attached to these function-based parameters. So that goal addresses a functional problem, and the objectives tell us what will be done to improve that function. All right, so then this framework provides just a form that you can organize all that and put it sort of in an assessment table. So when you are doing your baseline assessments, you would populate this with your function-based parameters, the measurement method that you would use, the value from the field, and the rating. So for example, if you were doing floodplain connectivity, you might measure the height of that floodplain relative to the bank full depth. We call that the bank height ratio. You would put the actual measure here, and then, so if it was 1, that means bank full is the top of the bank. You're very happy. And for the rating, you would put functioning. If it was 3, that means the floodplain is 3 times deeper than bank full. You would put not functioning here. And then in your monitoring years, you just keep monitoring that, and you look to see how these ratings change. So what you want to see are parameters that are going from not functioning to functioning, or functioning at risk to functioning. That delta is functional lift. And most practitioners, any practitioner who's using natural channel design is already measuring these parameters. This is just reporting it in a different way and getting away from just talking about and showing dimension pattern profile. We're linking that to these parameters. Yes?
How do you separate monitoring water quality improvements from adjacent to the restoration versus what was already in the channel upstream of the reach? How do you separate the improvements that you see?
Like what Kurt was showing, like upstream, downstream monitoring.
Okay, so then how do you
it is where goals and objectives are important, because like Kurt has shown with some of his data, he is seeing improvements, but they're not back to reference conditions. So what would be a goal? Like, do you just want to see improvements? Or if the goal long term is to get it back to reference condition, then you kind of come back to that, well, you need more reach length, more watershed treatment, and time to make that happen. All right, so the other concept I just wanted to mention was restoration potential. So restoration potential is a combination of these three things, and it sort of hopefully begins to pull some of this together. So to determine the restoration potential for our project site, we need to know what the health of the upstream watershed is, what the baseline condition is of our project reach, which is the form I just showed, and then the constraints, because a lot of times we have constraints. The landowner will say, your corridor width can only be this. You can't have as much land as you want. Or I already have a road, or I already have a sewer line, or whatever. So the restoration potential answers this question. What is the highest level of restoration that can be achieved based on the watershed condition, the reach condition, and the constraints? If we will answer this question honestly, we will avoid projects like the brook trout project I shared in Baltimore. They would not have ended up with a goal that was to have brook trout actually in their stream because of this piece. It might also help us with some of our biological and chemistry goals if we have too many constraints. Okay, so now I'm going to get us back to Swamp, get onto the site, kind of show how some of this might play out on the projects that you've heard described so far. I just want to take a poll. Both Eddie and Kurt referred to priority levels. Is anybody not familiar with the priority levels of restoring incised streams? I won't spend too much time. Okay, so let me walk through this. I'll do it fairly quickly, but some of you, this isn't familiar. So basically, Roskin put together a framework on a hierarchy of restoring incised streams. So 1 is the highest level of restoration. 4 is not restoration. 4 is stabilization in place. So 1 means reconnecting the stream to the original floodplain and constructing a meandering channel. This is assuming an alluvial valley. 2 is to excavate a new floodplain and construct a meandering channel. 3 is to create a step pool channel with bankful benches and low sinuosity. And as we mentioned, 4 is just to stabilize it in place. So a couple of...
exist in a 1,000-yard stretch, all those
doesn't matter. It's not really dependent on the reach length, although I will say from a practical perspective, to do a priority 1 or 2, you want to have some length. Again, it also is in low gradient stuff. So if you're working in some of your trout streams that are steeper than 2% slope, this really wouldn't apply.
So it goes this, so you have steep slopes and flat slopes.
So this is, I'll walk through each of them. So the priority 1 is you would take your channelized stream and fill it in. In order to pull off a priority 1 and raise the stream, you have to go upstream and find that fall. So Duke Forest is full of great examples because downstream of every culvert is a 3-foot fall and it's incised. So that's 3 feet we can make up immediately. So what we would do, if this was the culvert, we would come offline and set the elevation of this channel equal to the culvert. So all that drop goes away. You'll see the examples when we go out in the field. And then you build your new meandering stream, and then yes, at the lower end, you have to step it back down. So you create another step pool channel at the lower end. And then you can fill this in, turn it into wetlands, make all of this a floodplain. So you will increase flooding if you do a priority 1 by design. So you have to be sure that your landowner will allow you to increase flooding. A priority 2 is generally done when you don't have that big drop upstream. It's still a small stream. Priority 1s and priority 2s are generally performed in fairly small streams, primarily for the 1 because that's where you can find that drop or that head cut. And in priority 2s, because it's expensive. When you start excavating floodplains, you're moving earth. So in this case, we are carving out a valley and then putting that meandering stream, filling in the old channel. And then the priority 3, you're really kind of keeping the stream pretty straight and dissipating energy with more of a step pool bed form than a lateral meandering bed form. Okay, so now we'll apply this to all this stuff to the projects that we've seen and described so far. I'm not going to talk about the wetlands since that's not a stream part. I'm going to primarily talk about the phase 2. Are we calling that phase 2? Okay.
1.
So we're calling this phase 1. So 2 equals 1. And 3 is 3.
From that, 1 and 2 got mixed up because they were both to be built and there was a delay. It doesn't. 1 is the stream, 2 is the dam. Everything else is the same.
Plan sequence and that the sequence are flipped.
Yeah, I thought I had that straight after our last meeting, but obviously I do not. Okay. So this is the first stream part, phase 1. You've already heard it described a little bit by Eddie and then in more detail by Kurt. He showed the data. I just wanted to sort of walk through these and do 2 things. I'll refocus, re-describe these projects using this framework so you can kind of see how we might focus on the function-based parameters, and then throw in a few lessons learned, because some of these projects are pretty old, and if we had to do it over again, we would do some things different. So for the phase 2, and you heard Kurt mention that, reconnecting the stream to a floodplain was one of the goals. That is a level 2 goal, floodplain connectivity. Improving the bed form diversity. That means improving the riffle pool sequence. The way we did that first was through the floodplain connectivity, reducing shear stress, reducing the forces, the hydraulic forces in the channel helps to allow those bed forms to form on their own. We also added pattern, so adding sinuosity helps to create bed form diversity. Reducing bank erosion. Again, one of the big ways that we reduced bank erosion was back up here with the floodplain connectivity. So I hope you're beginning to see how a level 2 function is supporting a level 3 function. By improving floodplain connectivity, we reduced the depth of the channel, which reduced the bank heights, which helped to create stable banks. We also put vegetation and other structures to help as well. And there's a pretty big goal here as well, to reduce nitrogen and phosphorus levels. Kurt might say maybe the goal is not to reduce, maybe it's to quantify. This is more of an academic study, so you may not put the goal actually to reduce, but to see if there is a reduction. And in fact, we have seen a reduction, maybe not back to reference conditions, to improve macroinvertebrates. So again, the way that we would do the level 4 and 5 is by doing these level 2 and 3. There's nothing physically or directly that we can do to reduce nutrients and to improve macroinvertebrates. It happens with the floodplain connectivity, the bed form diversity, the lateral stability, and the riparian buffer. Those 4 activities that we can do help lead to the functional lift in 4 and 5. And we did have a bit of a constraint with this project. Kurt was our constraint. Kurt said you can't have the whole floodplain. Like we wanted to do pattern all over the floodplain. Can't have the whole floodplain because I'm going to do those wetland terraces that he mentioned. So he took most of the floodplain with his plots, and we actually put the channel back into close proximity to a remnant channel. Now, was that remnant channel an original channel? Probably not. But it matched pretty closely the dimensions that we felt were the appropriate dimensions. And so the biggest constraint would be we had a little bit lower sinuosity than what we might have done if we had the whole valley. All right, so lessons learned from phase 1 would be to design a smaller bankfill channel. So this is a fairly urban watershed. When we did this project, we were still a little bit more in the urban enlargement camp than we may be today. So if I had to do it over again, we would have looked even closer at the sediment supply and the forces in that channel, and we really would have asked the question, could we make this cross-section smaller? And we've learned, I'll show you in the next slide, if you design tips that we've learned to kind of guide us with the design size. The other thing I would have done is use more large woody debris. We are working right now on creating a performance standard for large woody debris. We're using a large woody debris index that was developed by the Forest Service, and right now we're focused on headwater mountain streams. So we are literally backpacking into pristine areas, fairly pristine. We've done a lot of work in Basin Creek, if you're familiar with that, near Stone Mountain. We are scheduled to go to Joyce Kilmer, which is an old growth forest. But we're also going to do crappy forests, degraded forests. And we're also going to do restoration projects that are 10 years old or more, because some of those projects have a fair amount of wood. And we're going to use this index as a guide for how much wood we should be putting in the different stream types in different landscape settings. So I'm pretty excited about that. Okay, so what have we learned about the channel size piece? What we've learned is that streams with a large floodplain and grade control can have dimensions closer to the rural curve. The rural curve is that regional curve that Kurt showed. It just means that we can have a dimension that's a size of a channel that's closer to a rural size than an urban size. But as that confinement increases and the density of storm drains increase, it begins to shift more towards an urban curve, which is about 3 times larger than the rural curve. And so that degree of confinement plays a large role in determining that channel enlargement. So the goal of the practitioner, to get those level 4 and 5 functions, we really want as small a channel as we can possibly get. And we will use this criteria in sediment transport, sediment supply, to help guide that. Okay, the next project that they mentioned was the stormwater BMP. So to put this in sort of the functional camp, reducing velocities from campus runoff would be a level 2 goal, and then reducing the nitrogen and phosphorus would be a level 4. And we had that constraint that Kurt mentioned, which was we had to have a channel, which we didn't want, because we knew that the main driver of treatment here would be more of a wetland. We wanted to slow water down, create as much retention as possible, make surface water go subsurface, interact with the root zone of those plants to get the level 4 treatment. But we couldn't do it for permitting purposes. They have started working to get around this somewhat in the Virginia and Maryland area. So some of you may be familiar with this. It has a couple of different names. One is this regenerative design, and regenerative design has kind of 2 settings. One is more of the urban stormwater BMP, which is ephemeral gullies, essentially, coming out of pipes, and you get this incision. And they are going back in these gullies and putting in essentially step pool channels. But their goal is to have water go subsurface as much as possible. So they are filling that valley back with sand and organic matter so that water stays subsurface, and they're trying to create the conditions needed to reduce runoff and to reduce nitrogen. So you can kind of see this is the after of this site. They bowl it out, they put their step structures in, they put their organics, vegetation comes in, and we could have done this. This is fairly creative because you can still call it a channel, right? It is a step pool channel. It's just you're encouraging water to be subsurface as much as possible. They might hit you here in that you're going from perennial to intermittent. That would be a bit of an issue, but they are doing this. It is not without its controversy. There have been a number of these that have blown out. Personally, and I have not seen these, so I can't speak from direct experience, but I like the concept. I think the solutions here are more in figuring out the design of how to build those steps so they don't fail and get their pool-to-pool spacing right. And when they can get that part structurally sound, I think there's some promise here in creating essentially more of the stormwater BMP that we wanted, but keeping it as a channel type than what we did.
But, if you spend $150,000 or $200,000 to put something like that in, they're not the sponsor is not looking for an experiment. They really like to know something that.
Oh yeah. If I was a client and I paid for it, I wouldn't want to see it blow out either.
So how do you know whether you stand a chance to, how high the risk is? The steeper the slope or the volume of water, how do you interact with those things?
Well, so those two things together equal stream power. So you could, slope and discharge are stream power. You could use stream power or shear stress as a guide. I think you could also, again, I don't know these folks super well, but I don't know that the pool-to-pool space, I think there are some geomorphology principles that they could bring in that maybe they haven't had yet as well. So
is there a higher failure rate in this approach than there is in other restoration approaches?
I can't answer that. I don't know what the failure rate is. Depends on who you ask. If you ask, what my experience, if you ask people who do this, they say the failure rate's very low. If you ask their competitors, they say the failure rate's very high. I do not know the true answer.
Now, one thing they are doing in some of these, I know what I read about, is they are putting wood chips and organic material below the stones to create bacteria, so bacteria can grow and basically get some treatment as the water filters down through them.
Right.
Stabilizing them on top and adding organic matter rather than just bare rocks.
And that's what they're doing. That's what they want. So those are the processes they want, and the form that they're building to get there, they still have some things to work out. They haven't all failed. So the one thing I would do is look at the ones that have not failed, look at the ones that have failed, and figure out what the difference is. Yeah, I think this is best for an ephemeral setting. We did get hit with a perennial call for the site that we were working on because there is, 200 feet, 300 feet of channel from our upstream end to the football stadium. Everything else is piped. And if they had just finished their piping job, we would have been golden. But you could go in that channel, and if you use North Carolina's method for determining perennial or intermittent, it scored perennial. Everybody agreed it was crappy perennial, but it did score perennial. That's where we got into that mess.
Anne Arundel County of Maryland has put together a design procedure for these regenerative stormwater channels that takes into engineering, all the power and stuff. So it's a pretty good design.
Is it?
It helps back up all the engineering that goes with it, the size of your foot of rocks and political spacing and all of that. So
Now, do you know that once people have sort of applied that standard of care, has the failure rate gone down?
I don't know.
So I think that's the question.
But I think it's getting better.
Yeah, I agree.
Every project, there's always some detractors.
Well, there are plenty of failures of natural channel design. So it's,
You could find.
yeah. And your point is well taken. Like if you're the client paying for this, you may not want to be the guinea pig. But I think both of these are far enough now along. You wouldn't necessarily be the guinea pig.
Well, if you've had one natural channel, big channel design that costs $250,000 or $500,000, then you don't want to have to follow it with the second one.
Right. I hear you. Kurt, yeah. All right, so last one is just, and you're not going to see this today, this is tomorrow. And this is that example where you had the 3-foot drop coming out of a culvert. This is the incised channel. So this elevation here is the same as the elevation of that culvert. So this is left as a big plunge pool. That's how we pull off the priority one. We make up that grade all at one time. And so this one has the potential for even more functional lift because you have great connectivity to the floodplain, a much smaller channel. You can see the wood in the channel now, the floodplain connectivity, the bed form diversity, the riparian vegetation, the wetlands from the old channel, the multi-state or the multi-thread channel coming in. And this, what you'll see tomorrow is somewhat closely related to what they call valley restoration that Art Parola has been pioneering out of the University of Louisville. And the one thing I really like about what Art is doing is that he is acknowledging that if you do not have sediment supply or you have very low sediment supply, you can build a very small channel. Most of us who are trained in natural channel design and come from that definition that I mentioned of dimension, pattern, and profile, so that the channel doesn't degrade or degrade. That is a transport-minded goal. You are thinking of transporting your sediment load, and you size your channel accordingly. And what Art's showing is that, well, if you don't have much sediment supply, or you can even deal with it in the beginning of your project, you will have more functional lift, especially in those levels 4 and maybe 5 as well, by creating a stream wetland complex. And we could do, I think that could be the next phase of here. Like what you'll see tomorrow, it is smaller than Bankful, but it's not as small as what Art would do. We did something a little bit different as well because Duke wanted to be able to monitor the water that's spread out. But I'm not going to be with you guys tomorrow, so I just wanted to point this out, that as you're looking at that project, which I think is an excellent project, the next evolution of that could be an even smaller channel, maybe several, where it is a true stream wetland complex for the whole thing. I mean, Art actually went the other way. This is a very urban channel. It was intermittent, and he rebuilt the valley. So there's gravel underneath the valley. There's wood. The channel is about 1/3 of the depth that we would have done as Bankful. The groundwater surface water interaction is exceptional, and it actually went from intermittent to perennial. They've seen temperatures come down, DO come up, fish come back in. So it's we would not have thought of that if you were trained in natural channel design, because we were focused on transporting sediment. But the truth is, in these small headwater systems, we may not need to be transporting sediment. So we should think about this and kind of keep this in our toolbox. All right, so this has also been pioneered in North Carolina. If you look at some of the headwater coastal plain work, it's essentially the same thing, where they're building valleys instead of channels.